Okay, now we're doing number 7a. It's saying you have a 7 Newton Coulomb charge is located one from this. They said find the electrostatic force that one particle exerts on another. Remember that now the formulas which we have, let me go right in the front page maybe. Even here we can write. So it's going to be now for electricity. Remember that we have F is equal to KE. Okay, KE. Sorry for that. I'm going to say, let's get rid of this guy. It's equal to, said go. It's KE, then Q1, Q2 over R squared. Remember that these are only magnitudes. You are not taking the signs. And then from here, we also know that we had E is equal to F over Q. And then we then said E will be equal to KE, then 1Q, then over R squared. And then we had V being equal to U over Q, which means V was therefore equal to, we called it KE, then 1Q over 1R, right? Which if you're asked for the electric field at a point, we use this one, then this one for the V. Then if we're asked for force on a point, we use this one. So we first find the magnitude and blah, blah, blah. Let's not talk about it too much. We first find the magnitude and then we resolve, right? So then we have work is equal to F delta X, which we said our F, we get it from here, the formula for E. E is F over Q, which means F is equal to, you take Q to the other side, it will be EQ. So where there is F, I can also put EQ. So it's going to be EQ, then delta X. We normally write it as QE, then delta X. This is the formula for work. And that's the one we always use. Remember, to get delta X, you say final minus initial. And then we have the change in potential energy is just negative of the work done. Here we have. Then we can have the change in potential is equal to the change in potential energy over Q. This is the change in potential, which we know that change in potential energy is just negative work. So we can say change in potential is negative work over Q, which leads us to the final one where we say change in potential negative work is what? Is negative of QE delta X all over Q. Okay, well, that's the formula for work. And then Q and Q cancel. We have the change in potential being negative of E delta X. We have it. This is the change in potential if you want to calculate it. So basically, we are done. These are the formulas, okay? This one here, change in potential being negative work over Q. You can use it if they want work and you don't have E. You just take Q to the other side. Work will be QV, Q delta V, right? But you change the sign. So anyway, let's go to do this. What is the question now saying here? It's now saying a 7 nanocoulomb charge, blah, blah, blah. Find the magnitude of force that one particle exerts on another. Okay, so this is Coulomb's law. We see it's not QE because either we are using QE or we are using Coulomb. So it's going to be Coulomb, which is KE, then Q1, Q2 over R squared. Okay, we can say R1, 2, the distance between 1 and 2. What is our KE? It's a constant. You can go and get it from the front of the paper, which says KE is 8.99 times 10 to the 9. So it'll be 8.99 times 10 to the power of 9. Then you have Newton meter squared per Coulomb squared. This is all times Q1. Q1 is going to be 7.50 nanocoulombs. So we can say this times 7.50 nano is times 10 to the negative 9 coulombs. Then we say times 4.20 nano, which is 4.20 times 10 to the negative 9 coulombs again. And this is all over their distance. The distance between them has been mentioned here that it's 1.80. So it's 1.80 meters squared. Don't forget to square it. And then we can get our coulombs. Then is this force attractive? We can go to II. Is the force attractive or repulsive? We say the force is repulsive, because if we can see this, both our charges are positive. This is a positive value. This is a positive value. So both our charges are positive. So the force is repulsive. Then they said, what happens if both charges are negative? If both charges are negative, the force doesn't change. if both charges are negative, okay, and negative, the force remains repulsive. Okay, the force, the value does not change. Okay, the value of the force, or the magnitude, say the magnitude of the force remains the same. The magnitude of the force remains the same. Okay, remains the same, and the force is still repulsive, and the force would still be repulsive, because they are both negative, would still be repulsive. Okay, because they are both negative. And then we can go to, do we have anything else? We go to part BI. Okay, let's go part BI. Because of the length of this video, I'm going to pause it here and do part BI.